first video in a short series of video on research design and quantitative methods is an introduction to experimental design. And before we look at specific experimental designs, we first have to know about inference in quantitative methods. So when we are going from design all the way to conclusions based on data, we're going to be making major inferences. That means that we are going to be planning and carrying out a research project that takes data about something, some measured information, and collects it, analyzes it, tests it perhaps against certain hypotheses, and draws conclusions from it. At all of those points, there are inferences. And the first one, the main one that we're going to be talking about in this series of slides is internal validity. There are other kinds of inferences, and you will probably also have read or will read about inferences particular to measurement. Inferences about measurement are slightly different. They really all revolve around construct validity. But so for the time being, what I really want you to focus on is internal validity, which is particularly the inference about validity, the whether or not the decision based on data is valid or correct when that decision has to do with a causal relationship. So when you make a claim that X causes Y, that X has an impact on Y, that X affects Y to some degree, you are making a claim that has or has not internal validity. It may or may not be correct in terms of causation. So we mostly want to do this when we have an intervention. So we have done something to improve, to cause a change in participant outcomes. Sometimes we actually want to do that in field settings. So in the field, you may be interested in testing out some program, either to impact student achievement, motivation, teacher persistence in the field, etc. Now, when you have done something which you hope will make an impact on an outcome, you have to try to answer the question, was it actually what I did, my intervention, or was it something else that caused changes observed? Now, it is possible that, in fact, there is a different cause than your intervention. It is also possible, of course, that you didn't observe any changes, in which case you don't possibly, well, you could possibly have an effect, but we're not going to concern ourselves with that. Anyway, you're not going to feel confident drawing a conclusion about the effect. But if you appear to be able to claim that there's an effect, the question is, what caused it? And we use experimental design because it improves our ability to attribute an effect to a cause. So what are the essential characteristics of true experiments? You probably know these back from high school science. Okay, so the main characteristics are random selection. Every member of a big population has an equal chance of being selected to participate in the study. So if your population is first-year teachers in urban settings, then theoretically, random selection would mean that every first-year teacher in urban settings across the country, let's say we're studying America, we were limiting our population to the United States, were assigned a random number, and then you used a random number generator to select teachers. Now, we're not going to do that. We almost never, particularly in small number research, have the availability to do that. So it's almost an assumption that we're not going to use random selection. And one thing you can do is you can limit the population that you claim, but also it's just kind of so rare that we try to have a large sample, and we just move on, frankly. It is an essential characteristic that you have an independent variable with at least two conditions and that you can manipulate that. So, for instance, sex at birth is not a factor in an experiment because you can't manipulate it. You can't change it on a random basis. Whereas whether someone is in a writing workshop or a non-writing workshop form of writing and structure is something that you could manipulate. You could put some people in one and some people in another according to your control as an experimenter. And then with an experiment, you are going to assign people to one of those two conditions. Okay, that's your manipulation, is that you are able to assign people to the conditions, and you're going to do it on a random basis. So every individual who's participating in the study will have an equal chance of being assigned to either the experimental, for instance, the writer's workshop group, or the control group, what we call business as usual, usually in education. And it's the random assignment that lets us call the design experimental. So desirable characteristics, controlled manipulation, okay? That is the researcher actually delivers the intervention. This is one of the big things in field experiments, where usually for a variety of reasons, schools, for instance, will not allow researchers to come in and, for instance, take over the class. So what we often do is, if we're working with teachers, we are going to ask teachers to play a part in implementation. And if you do that, when you write your procedures section and when you plan your procedures section, the training of the people who are actually going to administer the intervention, whether they're research assistants or teachers who are working on the project team, whatever they are, they need to be carefully trained, and you need to be able to document that. You also, a desirable characteristic is that you have control over what we call extraneous variables. That's variables that are not things that you intentionally manipulate. This is why true experiments in psychology so often appear out of field settings and in laboratories, because in laboratories, the researchers can pretty much control everything, at least about the environment. So if you have, let's go back to writer's workshop, and this would have to be, when it was a new experimental program. If all people who were in writer's workshop classes were also in classes, let's just be really obvious about it, in charter schools, whereas all the people who were in business as usual were in regular non-charter public schools, then the nature of the school organization would be entirely confounded with the writer's workshop, and you would not have internal validity. That is, you could not claim that if you found a difference in outcomes between the writer's workshop students and the business as usual students, that it was not due, in fact, to charter school versus non-charter school. So you'd have a complete confound. Sometimes this can happen in a less obvious way. So sometimes say that you have an experimental program and a control group to compare things to, and you've used random assignment, but just by chance, several of your schools that have been randomly assigned to the experimental condition have administrative change, which, as we know, disrupts school operations considerably. Then administrative change might be a confound to any results that you have. And then you really need to document that and hope that it doesn't interfere with your results, but you can't dismiss the possibility, no matter what, that it has. So you need to document it carefully and hope that you can still get published, essentially. Now, even if you have true random assignment and good experimental manipulation and no interference with quality of the manipulation, no confounding variables, you can still have threats to the conclusions about causal effects in an experiment. And we talk about things that can interfere with the conclusion from an effect to a cause as threats. These are things that can reduce your confidence in your causal claim. There are other things that could account for causation. And with random assignment, we assume that the groups will differ only by chance. Statistical, because of the distribution of standard errors, if you have a large group, then your standard errors are going to be small, and chance will play a small part in any differences between the groups. And relatively speaking, any differences that are due to your manipulation or your intervention should play a large part. However, some things can happen that are outside the control of the researcher, the manipulation, and the assignment. The main source of these with true experiments are what we call social threats. So social threats can happen even when randomization works. And the social threats are rather cute, and at least in terms of their names and occasions when this happens. So one of the social threats is called a novelty effect. And it's similar to something that you can look up called the Hawthorne effect. Novelty effect is just, in fact, new experiences often will cause changes in motivation, regardless of the nature of those experiences, just because they're new. So if your outcome variable is interest, engagement, motivation, and you're comparing it to a business as usual condition, then your students, if they are the target audience, may just kind of get a wake up. Oh, this is something different. We're going to try it out. Another is experimenter expectancy, which is that if an experimenter is coming in and delivering an intervention, then, and it's a regular person who is delivering the control condition, first of all, people may play to the experimenter. There are other kinds of effects. The lab coat effect, that people may be nervous because of the experimenter. People may do what's called hypothesis guessing. This is not going to happen very much in education, where people try to guess what they're supposed to do. In education, you don't see some of these things so much because if you're looking at achievement, it's hard for people to kind of fake that. But if you're looking at something like motivation, interest, engagement, then the novelty effect and experimenter expectancy can definitely happen, where people either are excited or they play along because of what they kind of think that they're going to be rewarded for, even if it's just psychologically rewarded for. Diffusion or imitation of treatment is particularly an issue if you're doing experiments in one school with multiple classrooms. And that is when a teacher goes into the lounge and says, I'm in this experiment and it is so cool and we're doing such great things. And all the people who are supposed to be in the business as usual condition say, give me some of your materials. Tell me what you're doing. How is this running? What do you do? And you tell them. The control condition, sometimes it's a school principal, says, I see that it looks like this is working really well in the experimental classes. Oh, I don't want to just keep it for the experimental classes. I want to tell all the teachers. And while that is a great ethical practice, it ruins the experiment. So now you're unlikely to find a contrast between the conditions. You're unlikely to be able to claim that your intervention did or did not cause any change that you find, because in fact, everybody was getting the intervention. In the previous conditions, say you get a bump in interest associated with the intervention. Well, that may just be because the targets of the intervention were unusually excited. In this case, you're unlikely to see a bump in the variable like achievement or motivation, because all of a sudden everybody is getting the treatment. Compensatory rivalry is when, or which is also called the John Henry effect. Again, something you can look up. John Henry was a steel driving man, and you can look up the song even. Compensatory rivalry is when people in the control condition realize they're in a control condition and realize that they are not receiving something so-called special that other people are receiving, and they're angry, and therefore they work really, really hard to prove that they can. There used to be I think it was a car repair commercial about we're number 2, so we try harder. Resentful demoralization is the same circumstance, but the opposite effect, which is that the people in your control condition get angry because they feel like they're being withheld some beneficial treatment, and they resent it and they just kind of go on strike. Either one of those could affect any possibility you might have of finding differences in your dependent variable between your treatment and your control condition, or attributing those to your treatment or control condition when in fact it's because of varied efforts simply due to people's social understandings of being in an experiment at all. And compensatory equalization of treatments is, for instance, it's a little bit similar to diffusion or imitation. It's the, for instance, the principal being unhappy that some of the students are receiving a special experiment and some of the students are receiving business as usual, and deciding that the people who are receiving business as usual will get a different special treatment. So you're not comparing treatment to control, even though that was what you were going to claim. Little did you know, but the principal was giving these other classes something special. You could say that that was a failure to adequately manipulate treatment. And there's some bleed over between the names of these threats, the way these threats are described, and anything else. It's a taxonomy and a classification system, and it doesn't always work perfectly. So don't swear by these names. But the general idea is that something is going on having to do with people's social understandings of what it means to be in an experiment at all, that is not relevant to the nature of the intervention you're trying to manipulate, but does have a relevant effect on your ability to claim your intervention as the cause, and therefore is a threat to internal validity. I'm just going to go a little bit briefly into notation for research design. I hope it's brief. This video is probably already long enough, but in research design, one of the classic ways of drawing these out is to use an R for random assignment, an O for an observation or occasion of measurement, an X for exposure to a treatment condition, and A, B, or C to indicate each group that participates. So for instance, your most basic and not particularly good randomized designs, you'll see the R that tells you that you've got a randomized design, a treatment, and a control group. And under number 1, which is treatment and control post-test only, the treatment group has an X for having received the manipulation. The control group does not have an X. And after both of them, there's an O, which means that both of them have been observed or measured. The problem with this is that you don't know where they started. Okay, so this is actually a pretty significant thing, is that even though you assume that they maybe all started at the same point because they were randomized regardless of group, you don't know whether their end point is interesting or just as expected without any manipulation. All you know is that they're different from each other, and that could be due to a host of reasons. One of the things in particular you don't know, and this is true for all the designs here, is whether or not randomization worked. That is, if you don't have a pre-test, an observation of the status of your groups before you manipulated your experiment, you don't, it still could be true that with randomization, your groups were different by chance, and you have no way of determining that. You also have no way of determining how large the magnitude is of any change that you find relative to what might be expected over a similar period of time. Just know that you have a change of the magnitude of the difference between the X group and the control group, but you don't know whether the difference between, you don't know the difference between normal expectations of normal growth and the particular growth that you found in the experiment. Didn't put that particularly well, but we will move on. The other conditions you see here is the multiple treatments group, which is you may have a case where business as usual either doesn't make sense. That would be with the control group. They would just receive nothing. Or in education, it's basically always business as usual, except in some cases like pull-out programs in special ed. Could be in professional development. You could have a true control group that received nothing. But there are a lot of times for ethical reasons, or just because you're looking at differences between different curricula, you want a treatment group A and a treatment group B. And obviously, the more groups that you have, as long as you can keep a good sample size in each group, the better your conclusions. When you have a pretest, that's very nice. It looks like one of my tabs with the pretest, post-test control got a little off, but in the basic pretest, post-test control, which is a great design. You know, that's basically kind of your bread and butter. If you can do a true experiment, is that you have randomization, that each group has an observation before the intervention and an observation after the intervention at the same distance before and after the intervention for each group. And then you can see whether the two groups differ on their pretest, which would be just by chance if they've been randomized, but you still want to know it. Whether the two groups differ at post-test, which you hope would be the place where you could make your causal claim, and also whether the treatment group had a change from pre to post. And if you were looking, for instance, at motivation, you would hope that there would be growth in motivation within the treatment group from pre to post. You can also go a little bit further, but I'll come back to that later. You can do the same thing again with, rather than a control group, a alternative treatment, and you can add in treatment conditions as feasible. If you have multiple pre-tests or post-test, that's really nice. One of the things is that you can look at whether or not your outcome is stable over time. And you can also see particularly whether a change in your immediate post-test is due to something like novelty, in which case it would expect to wear off, whether it maybe is related to the way such and such was increasing anyway, and again, not attributable to what you actually intervened with. And so this is a nice design if you can afford it, if you can actually do follow-ups with your sample size. It is a more powerful design. And if you're interested in stability of a change over time, it's definitely desirable, because we probably have too many treatments that wear off. But a powerful treatment really should change a long-term trajectory. Again, this is difficult to do unless you have the ability to follow up with people for a while. Now, some of these things that I've already talked about, you can do approximately now, given your statistics or where you were about to be. So if you're looking at post-test only treatment and control, so you have two groups, each of which has been observed on the same variable, like the dependent variable, achievement, motivation, whatever, and you have two groups, each of which has values on that independent variable. You have a test that you can do. Think about it. I'm using wait time. What is that test that you can do? That's called independent samples test of means, the t-test. So is number 2, where you still have two groups. Each of them has been observed on the same variable, achievement, motivation, whatever. You are comparing those values between the two groups. The two groups are independent, means that nobody who is in group A is also in group B. And that's the independent sample means t-test, different means. And the third, which you may have gotten to or will get to soon, is when you have one group and you have a pre-test and a post-test. So all you're seeing is whether a difference in a score for a single group is statistically significant. And I have this down as being randomly assigned, but that doesn't even make any sense. That doesn't actually belong on these slides because it's not a true experiment, because you can't randomly assign people to one group. But I'll mention it anyway because it is a design that you could do if you have one group that is being measured twice. Then you can take the post-test score, subtract the pre-test score, and you have a dependent samples, also known as a paired sample, also known as a test of difference. Usually I call it the dependent sample means test. It's a t-test. You can also think about extending your stats. Again, this is the little slide where I've got my R's and my O's not lined up correctly, but you have random assignment. You have a pre-test and a post-test for each group, your treatment and your control. Number 5 below shows the same thing as a treatment and control, but a treatment group A and a treatment group B. It may be easier to see because all my tabs are lined up. So you have random assignment, you have a pre-test for each group on the same variable, same test, say a survey of interest in science. Then they go into 2 different experimental conditions that you manipulate. One of them is simulation of simulated dissection. It's life science. And the other one is live dissection, which isn't really an experiment, but bear with me here. And then you give them a test at the end, which is a post-test. So it's also on the same variable as the pre-test, which was, I think, engagement in science. All right, so you have a pre-test and a post-test, engagement in science, and you're looking to see whether the change in engagement in science is different for one of the 2 groups. And is also, the change is different. So first of all, is there a difference between post-test and pre-test for either group? And then is there a difference in that post-test minus pre-test or change between the 2 groups? So you have multiple comparisons. What you can do, first of all, is you can do each separately. You can just look, as with a single observation, you can look at the difference between the second observation for group A and the second observation for group B, independent samples t-test. You can look at the differences between the pre-test for the two groups to see whether or not randomization worked. They should be equal. You could look, for instance, at within just group A, was there a significant change from pre to post, or within group B? This is a lot of tests, and it probably doesn't get to your big question, which is the change, the growth, you hope, in STEM interest attributable to the difference between treatments? And that's what we call a change of change test. You probably haven't studied it yet. You may not actually study it this semester. It's really a very simple test. And conceptually, it's very much the same in terms of design. So this isn't a stats class. We don't have to talk about the stats, but it is just adding extra things, 2 observations for each variable and 2 different treatments with random assignment. And so if you wanted to make the inference that the growth in STEM interest was greater for treatment A than it was for treatment B, this is the design you'd use. And as long as you had controlled for social threats and you'd use random assignment, your inferences would be pretty safe based on whatever data you collected, given a couple of the other consideration of some of the other threats to validity. But your inferences about cause and effect would be safe if you've controlled for social validity, maintained your random assignment, and maintained fidelity of implementation and done random assignment, you'd be good. And that's the last of these slides for this presentation. Thank you for your patience.